Beam is the result of the evolution of data processing tools, starting from some tools that Google has built. It all started back in 2004 with MapReduce, which was quite a revolution at the time, but really it's a huge select and a huge group by done in a distributed and fault-tolerant fashion. So it's kind of the assembler of big data. Inside Google, it evolved in two directions. First, it evolved into providing a high-level API on top of it, which is Flume Java, which has a very similar API to Spark and other popular tools. The other direction was supporting computations on streams. This was implemented in Millwheel, which innovated in the direction of making computations on streams deterministic, whereas previously it was commonly thought that computations on streams inherently have to be approximate. Then in 2014, these two converged and ended up in a tool called Cloud Dataflow, which innovated by providing a programming model in which the difference between batch and streaming does not exist. So it does not make sense to ask, is this a batch pipeline or a streaming pipeline? It's both. And it also aimed to be portable across languages and across multiple possible ways to run pipelines written in these languages. And then it evolved further into Beam, which is basically an open sourcing of the Dataflow SDK, but much more driven by the community. It's independent on a particular vendor. For example, I think about a third of the committers are Googlers. So it's truly a community-driven Apache project that is evolving further in the direction of portability and providing a good standard programming model for big data. Beam's main point, compared to other data processing frameworks right now, is that the distinction between batch and streaming is non-existent. Another way to phrase that is that batch workflows are nearly always just part of a higher level streaming workflow. For example, invoking something repeatedly on new data or repeatedly on all data accumulated so far. We will see this referenced later. Another important point of Beam is portability, which means that the Beam model itself is not tied to any particular language, and there are SDKs for Java and Python and one in the works for Go. And this all gets compiled to the Beam model itself and can be executed by multiple runtimes. Currently, there is something like 6 or 7 different runners. About maybe 3 or 4 of them are actually production ready. And so this is Beam's vision, that it is cheap to add another language and cheap to add another runner. The foundation of Beam is something called P-transforms, which are transforms that take logical collections of data and produce other collections. They are all built out of 3 primitives. One is called Pardu, which is basically flat map, familiar to anybody using any other data processing framework. The other is group by key, that takes collection of items and groups them by key so that you can later process each group in parallel. And the third sort of primitive is grouping transforms into composite transforms so that it appears like one transform. At a high level, the Beam ecosystem can be seen like this. At the bottom, there are various runners that can run Beam pipelines. Then there are SDKs that expose the Beam model under idiomatic language-specific ways. Then there are libraries of useful transforms, including transforms for getting data in and out of pipelines called IOs in Beam. And on top of all that is user code. Here is an example Beam pipeline. On the left is its graph. Of course, pipelines don't have to be linear. It's just the classic word count example. So we operate in terms of collections, and we apply transforms to them. And typically somewhere at the edge of the pipeline, but not necessarily, as we'll see later, is getting data in and out or interacting with external storage systems. In this case, we're reading and writing files, which is pretty common. So our talk will be focused on I/O. And let's talk about why it is such a big deal. On the surface, it does not seem like such an interesting topic. Like, few people write papers about how to get data in and out of pipelines, whereas people totally write papers about programming models. But we'll see that this is as important. Beam has quite a hefty collection of connectors to various storage systems, various kinds of file formats, various kinds of file systems, various kinds of streaming systems, and systems that are just like databases that contain data at rest, and so on. The first thing to know about I/O, or to understand about it, is that it is obviously essential to pipelines. A great majority of pipelines that we see in practice are people taking data from one place, doing some fairly simple transformation, and writing it to another place, which is known as ETL, extract from one place, transform, load into another place. So I/O has to be good if you have any empathy for the users, because this is what users are actually doing. The other point is that I/O is a really messy part of the whole picture. In the whole ETL scheme, the T part is implemented by a pure programming model that somebody probably defended a PhD about. So it is a good abstraction. It's proven to make sense and so on. And the E and T parts are, nobody wrote a paper about that. They're usually considerably more messy, considerably more diverse in requirements, and considerably harder to get right. For example, there are hundreds of different exotic requirements that people place on reading and writing data. You might want to read from a database via a CSV dump from the database. You might want to decompress files. You might want to stream new files as they appear. You might want to rate limit or throttle yourself when interacting with an external system. You might want to read multiple database tables in the same transaction, and all kinds of things like that. So the set of requirements is as diverse as the set of systems that you interact with. The next important point is that I/O is unified, just like the rest of the programming model. The programming model does not contain a distinction between batch and streaming, and so should I/O. Typically, people tend to think about I/O in terms of, oh, this is a streaming system, this is a batch storage system. A batch storage system contains the data as a block. A streaming system gives you changes. But really, typically, you're dealing with a situation where you need to process some historical data and then carry over and continue processing new data as it arrives. You very rarely want to just start from an arbitrary point in time and start ingesting new changes, not caring about exactly where you started, and not carrying over previous processing. For example, if you're reading files, you probably want to also stream new files, maybe in a configurable way, and maybe in a particular situation you don't want to stream new files at all, but in general, it would be just a special case if you don't want to look for new files. When you're reading a Kafka topic, this is not really a purely streaming use case because you have this huge change log accumulated in it so far. And for example, if you find a bug in your algorithm, you may want to reprocess the whole thing from the beginning, which is more suitable for the way a typical batch processing framework executes things. So I/O is also a concept that's agnostic to batch and streaming, and you should think about it in this way. So typically, pipelines are taking an evolving input and compute an evolving output from it. And the function of the pipeline, the purpose of the pipeline is to keep output to be consistent with the input in some way. And for people who attended the previous talk, a great way to think about this is this stream and table theory. In this sense, you're really ingesting the changelog of an input, and you're producing a changelog of mutations to the output. Whereas the input and output are data at rest. Another thing interesting about I/O is that it is absolutely unforgiving. Any bug in an I/O connector is data loss. And on our team, that means drop everything you're doing and go fix the data loss. You need to be very mindful of fault tolerance. For example, if you write a record to a database and then you crash and you write the same record again, what do you do with that? How do you do exactly once reads and writes? How do you handle failures? I/O is the part that is likely the most performance critical, and it's hardest to make it perform well because it's so diverse. So I/O is a really interesting area to work in because of these requirements, and together they necessitate having very good abstractions for I/O, because without good abstractions, you're going to be lost in this. In other words, it is a chance to do better than the state of the art for abstractions provided for I/O by many data processing frameworks, including Beam until recently. As I said, nobody writes a paper about their I/O APIs. In the MapReduce paper, it's a couple of paragraphs. Inside a many-page paper, inside the Beam, Spark, and Flink papers, there is not a single word about how data gets in and out of pipelines. They have an API for that. The API is just not glorious enough to include it in the paper. Unfortunately, that leads to a situation where people's requirements for I/O are too diverse for the framework to support them all out of the box, but the APIs are too rigid for users to build it themselves. So it kind of feels like people started with creating a big data programming model and then thought, actually we also need to get data in and out of the pipeline. Let's add some APIs for that and we'll be good. No offense, because again, this was exactly the situation in Beam as well until quite recently. In other words, I/O begs for good abstractions, and that's what I will be talking about in my talk. Let us begin. So as I said, traditionally it is thought that I/O has to happen at the boundary of a pipeline. So you have sources and you have sinks, and sources are something that is just configured in a certain way and returns you the data. For example, it's configured by a file pattern or a topic, and it gives you the data from those files or that topic. And likewise, sinks are something that takes the data and it disappears into the sink, and it's written and you're good. Various frameworks have different APIs for that. In Spark, for example, sources are implemented using something called receiver. In Flink, it's source function, MapReduce, it's input format, and so on. These APIs are quite ad hoc, and they're very different from the rest of the programming model, more like they have nothing in common with it. And they don't compose with it in any way, except that you can process the data that it returned with the rest of the programming model. This idea of providing ad hoc APIs for I/O breaks down very quickly. For example, the moment you have a use case when file names come on a Kafka topic, you can no longer use the standard I/O API to read those files, because you're no longer at the edge of the pipeline. You're reading something from Kafka, and only then you want to read that from files. Likewise, sinks are not really at the end of the pipeline. For example, if you're writing some data to a table and some records don't match the schema, you probably don't want to discard them. You probably want to return them as a separate data set and write it somewhere else, the so-called dead letter approach. Or maybe you want to just kick off some further processing after the data is done writing, and it is a very interesting exercise to generalize this idea of do A then B to a streaming pipeline. It is possible to generalize it, but I will not mention it here. So my point is that really I/O is not different from the other transforms, and it has to be just another data processing task. For example, the idea of reading files is just a transform that takes globs as input and returns records in the files that match those globs as output. Reading from our results of a SQL query or a set of SQL queries is a transform that takes various parameters to pass into a query and returns you all results of those queries with those parameters substituted into them. If you're importing into a database, you take rows as input and you return invalid rows as one output and some statistics of the input as another output. So use your imagination. The point is that there is no such a thing as being at the edge of the pipeline. I/O is just another data processing task. And once you adopt this approach, you realize that you've been missing out on so much by using the native IO APIs. And all it takes to not miss out on that is to just stop using them and instead write your stuff using the rest of the programming model provided by the framework. The main thing you've been missing out on is composability, also known as hackability, like the ability to assemble what you want from a number of blocks. And if your blocks can only appear at the edge of the thing you're building, you can't build very much. Imagine a puzzle that only has edge pieces. The second thing is automatically you get unified batch and streaming semantics. You automatically get the benefits of the fault tolerance of whatever framework you're using. You automatically get scalability. For example, a commonly asked question on Stack Overflow is, how do I read 1,000,000 files with Spark or with Flink or with Beam? And if you're using a runner that treats every file as a shard, because that's what it's taught to do using the native IO API, like when you read files, you produce one shard per file, and every shard reads its file. Then you have performance problems because you have 1,000,000 shards. However, if you think of reading 1,000,000 files as just the problem of processing 1,000,000 elements, where every element is a file, and processing it means reading records from it, then it's a problem of processing 1,000,000 elements, which is tiny by standards of all of these frameworks. You automatically get monitoring and debugging and various orchestration, and you automatically get all future features that the framework is going to provide in the future, whereas IO APIs evolve less frequently. And again, all it takes to enjoy these advantages is just to start thinking about IO differently. Nothing needs to change in the framework. That is the way in Beam currently. For example, when you read from the results of a database query in the Java SDK using JDBC, it expands into a transform that creates a single element collection with the query, then it executes the query, and then it adds a repartition transform to make sure that even though you read the data sequentially, you can process it in parallel. There are some considerably more complex transforms. For example, the transform that writes to Google's BigQuery is very, very complex. However, it also does a lot. For example, you can write different trackers to different tables based on the contents of the record. It generates temporary files and then loads them into BigQuery and then is able to clean them up when they're no longer needed by the rest of the pipeline. If the data is too big to fit in a single database import job, it shards it into multiple, and so on. So all of this stuff, it is certainly far from trivial, but implementing it using a rigid API would be simply impossible. And if you look at how BigQuery connectors look like when implemented using rigid APIs, they actually can't do this. For example, you have to do cleanup manually after you run your pipeline. Good luck doing that in a streaming pipeline. So composability gives you arbitrary power. You can assemble whatever you want, and no feature is too difficult for you to do because of the limitations of the API. The other thing is that composability implies modularity, meaning the idea that you can compose IO from together tempts you to also decompose it and wonder what else you can assemble from those bits. For example, if you look at how we can read text file globs and how we can read a Kafka topic, you may notice that they have a remarkable similarity. When you're reading globs of text files, you can think of that as a composition of expanding globs and then reading each file. For Kafka, you can think of it as a composition of listing partitions and then reading each partition. And the expanding globs and listing partitions part can reuse the same transform that repeatedly invokes a certain function and returns you new results of it. For example, you repeatedly expand the glob and return files that weren't present in the previous result. And you list Kafka partitions and you emit new partitions if new partitions appeared. So this transform can be reused. The transforms that read and write files themselves can be reused when you're importing or exporting data to something that has a file-based import or export process, like databases often do. This is certainly a case where you need the transform that writes files to return the file names it wrote, because you're going to tell them to a database and tell it, please import these files. So IO transforms are reusable, and it doesn't take a lot of imagination to come up with lots of use cases for when you would want that. Another case, this transform that imports something to a database itself can be composed with another one like that. If it returns something like a done signal, you can wait on that done signal and, for example, import into one table, and then when that's done, import to another table that has the first one as a foreign key. So composability rules, basically. And things that can be composed can and should be decomposed into smaller pieces that can be used more imaginatively. Now, as for what this all means for you, if you're both a library author or if you're a user, I advise to just ignore the native APIs for writing IO connectors provided by your framework and just do whatever you want using flat map and group by key and whatever else they provide. It's quite likely that this will be much easier to code. It's likely to be faster. It's likely to be more reusable in other contexts. If you're a library author, you should certainly remember that whatever you write has to be mindful of the idea that it's not exclusively batch or exclusively streaming, if at all possible. And if you're a library author, you should ruthlessly decompose the thing you create. For example, you should not create something that reads globs and returns records. You should think of it as a composition of a file operation that expands the globs and returns records from that, and so on. So try to find the little blocks inside what you're building. OK, with that in mind, let us see how it plays out in practice and why that seems to require a new programming primitive to play out in some situations. So here's how typical IO transforms look. A typical transform that reads from some storage system in parallel looks like this. We take the specification of what needs to be read, we split it into smaller specifications, for example, read individual files, or read ranges of files, and then we read each of those. A typical transform that writes to somewhere is often just a single flat map, and so why one would think that a sync API is needed is beyond me. And now we're going to look at more detail at the read part, because the write part is really as trivial as it seems. Let's look at these two familiar examples. Suppose you're reading a Kafka topic, and this part that reads a partition, something's off with it. Typically, a function that you pass into a flat map or in Beam Pardu has to return some results and terminate, whereas when you're reading a Kafka partition, the output is infinite and you have to keep tailing it. So it doesn't really fit the model of a Pardue or flat map as it stands. As for reading text files, you can get pretty close to doing good there, especially if you add another step that splits files into byte ranges or something like that. But if the byte ranges of the files that you read are fixed, then you will not be able to do this wonderful dynamical rebalancing that Dataflow does, where it dynamically repartitions ranges of data it reads in order to completely eliminate stragglers. And this is really important because, for one thing, it enables autoscaling. Being able to dynamically repartition your work is critical to be able to autoscale, because if you partition your work into 50 parts and then you realize you need 1,000 workers, you will only be able to use 50 of them. So dynamical splitting is really important, and again, Pardue/flatmap cannot do that because they process an element in a monolithic, indivisible way. So this is something that Pardue can't do. It takes an element and passes it through a black box and returns some outputs. That means that the output cannot be infinite, and that means that the act of processing the input for a single element cannot be parallelized further and like dynamically reshaped into something better fitting the cluster. We're going to fix this using this new programming primitive called Splittable DoFn, which differs from a regular DoFn by being splittable. In particular, instead of just taking an element and processing it, we're going to add another part. We're going to add a so-called restriction, which is also just a piece of data. So you can think of it as just processing a tuple instead of processing your original element. However, we're going to add some magic to make sure that the restriction can be dynamically split into more parts while the element is being processed. And that will give all the power we're looking for. So the element describes what work you're doing, for example, reading a file or reading a Kafka topic. And the restriction describes what part of the work for this element you're doing. For example, for a Kafka partition, it can be a range of offsets or just a starting offset. For example, if you're reading files, restrictions will probably be byte offsets. If you're reading from a big table or another NoSQL store, it's likely to be a key range. If you're reading a Kafka partition, it's also likely to be a range of offsets or just a starting offset. And more exotic kinds of restrictions are also possible. So when you process an element and the restriction using a splittable DoFn, the restriction is able to be subsplit into smaller restrictions that can be processed in parallel or be processed in sequence, but the point is that they can be processed independently. So it's no longer monolithic. The processing of an element is no longer indivisible. And of course, processing the parts together has to be equivalent to the original work. That's a given. For example, if you're reading files, the restrictions can be byte ranges, and different restrictions will cover different records in the file. They will cover, for example, the records whose offsets start in the given range. In this case, we're splitting our byte range into 3 smaller byte ranges. An unexpected consequence of this approach is that it allows infinite work per element. For example, a restriction that says read from offset 100 to offset infinity, meaning read the whole partition. This restriction can be split in 2, where one of them is finite, and that one can be completed. And the residual restriction is not finite, but we can apply the same process to it, and so by iteratively splitting it like this, we get checkpointing. So using this approach, we get the ability to do an infinite amount of work per element using the regular flat map abstraction. For future reference, this splitting process produces something called a primary and something called a residual. The primary is the part that keeps running. The residual is the part that can be processed separately, for example, in parallel. So to solidify the concept some more, if you want to write a new splittable DoFn, you need to answer the following questions. You need to decide how you want to process an element, what constitutes the work for one element. For example, if you're reading text files, the work entailed by that is to return all the records in that file. You need to figure out conceptually how this work can be done in parts. And it's possible that this work cannot be done in parts. For example, if this is a compressed file, there is no way to read ranges of a compressed file. But if it is, then you're pretty much on track to make it splittable. For example, if it's a text file, you can certainly read byte ranges. You need to decide how you're going to describe each part. just as a piece of data, what will serve as a description of every part. And then, of course, you need to write code that executes a particular part. And here is some pseudocode that reads text files in range start to end. You open the file specified by the element, and you seek to the starting point, and you read lines until you hit the end point. So I would like to emphasize that Splittable DoFns is a new API that allows you to express splittable work in this way. It does not automatically make DoFns that you wrote previously splittable. It's a new API. It's a new programming primitive alongside Pardue, group by key, and splittable Pardue. It's a third programming primitive. Let's focus some more on dynamic splitting because it's really the crucial part here. So suppose that you are currently processing a certain element in the restriction, and you've made some progress there, and you're going to make some more progress if you're not interrupted. And then while you're doing this, the runner decides that it wants to split you. For example, it seems like the work you're doing is going to take too long, possibly an infinite amount of time. So the runner would like you to terminate by some point, not necessarily right now, but fairly soon, or at a specified point. And the runner wants to execute the rest of the restriction somewhere else, possibly in parallel, or possibly after you're done, or whenever. This is basically work stealing, meaning that this is part of the work that you're planning to do, someone else is going to do it. Again, these two parts are called primary and residual, and a critical part of this is that this happens while you're processing. So the restriction that you're processing changes under your feet and becomes smaller, and now you have to process less than you originally planned. Let's see how this affects the code. This is like the poster child of Splittable DoFns, how you can read an Avro file using a Splittable DoFn. So you take an element that is implicit in the so-called process context, and you take a range that you need to read. You open the file, you seek to the beginning of the file, and you read full Avro blocks whose starting offset is in the specified range. And you output every record you see. Seems nice enough. Unfortunately, this end of the range can change concurrently. It can change after you checked that you're not past it. So this code is racy and unsafe. This turns out to be a surprisingly tricky problem to solve, but a solution exists. And the solution is as follows. Basically, there is two parties here. There is your DoFn that is processing the data, and there is the runner that wants to prevent it from processing some of the data, wants to steal some of the processing. So we're going to, and the runner wants to avoid returning something that you've processed, and you want to avoid processing something that was returned, because then you'll get an overlap between what you do and what the other worker does. We're going to solve this by introducing the idea of claiming work. Vaguely, this means that before you process some work, you need to say, I'm planning to process it, and sort of claim it for yourself. And the runner promises to split away only unclaimed work. In case of files, you can just say, I'm planning to process until this offset. And then the runner will split away only things after that offset. In the API, this is encapsulated by something called a restriction tracker that encapsulates the state of a single process call. It contains not only the original restriction, or more like not only the current restriction, but it also contains information about what part of the restriction is claimed. For example, if you're reading files, like up to what offset you have already said that you're going to do it until there. And as you process, you repeatedly claim so-called blocks of work. Yeah, you claim so-called blocks of work, and the restriction tracker either tells you, OK, you can claim this, I promise not to return it to someone else, or it tells you that, sorry, you cannot claim this. This no longer belongs to the current restriction. For example, because the restriction was concurrently narrowed. And that's pretty much it. This solves the problem of concurrent splitting. And this allows you to split away part of your work without waiting for anything that you're currently doing. It is a wait-free synchronization primitive, which is, I think, really important. And it gives dynamic rebalancing in Dataflow or in whoever else would decide to implement it, the ability to split work irregardless of the granularity of the processing. So you don't have to wait for anything to get to the next record and then check if maybe you should split. this happens fully concurrently. OK. With this API, here's what the read loop actually looks like. Instead of the restriction, you get the restriction tracker. And instead of comparing yourself against the end of the restriction, you ask the tracker to claim the block that you're planning to process. In case of Avro, the block in the meaning of the restriction tracker is literally an Avro block. In other cases, for example, if you're just reading text files, you can think of a single block as a single line in the file, so you claim each offset of every individual line. In case, for example, you've written a DoFn to watch for new files in a directory, each block can be one file. In that sense, one position is just the name of that file, and so on. So you say, I'm planning to do this work, and then you do it. Or the tracker tells you that you can't. That is it for the description of this abstraction. As for its role in Beam APIs, it is a fundamental building block for expressing splittable work. And this block is necessary to express some kinds of work. So partially, this is why Beam also still has the legacy native APIs for sources that were created before this abstraction existed. And this is why it is justifiable that other frameworks also have native APIs for reading data. However, I'm hoping that this programming primitive will be adopted more widely and thus enable greater composability in I/O. Basically, what it does, it enables writing composable transforms that read data. So it enables library authors to express the tasks of reading data or its various subtasks as composable building blocks. Now let's just quickly recap what we talked about. This all happened in the context of unification of batch and streaming, meaning that there is no such thing as a batch pipeline or a streaming pipeline, and likewise there is no such a thing as a batch dataset or a streaming dataset. In all cases, it's really streaming, but possibly with a bunch of backlog. That is also part of the whole thing. The second part of the context was that I/O is really important. That's what everybody does. It has very diverse requirements and is very messy. And it requires good abstractions because it's unforgiving to all kinds of mistakes. And traditionally, I/O is done using native APIs that are pretty rigid and cannot really they cannot really be composed with each other or much of the rest of the pipeline. And the analogy was that you have a puzzle that only has edge pieces, and that's not much of a puzzle. And we solved this by first introducing the idea of thinking of I/O as just data processing, expressing all I/O tasks using the basic programming model that gives you, obviously, the full power of the programming model and everything that comes with it for free, such as monitoring, debugging, scalability, fault tolerance, and so on. This way of thinking encourages one to create I/O in smaller and more composable building blocks. And finally, we talked about Splittable DoFns, which enable the point above for reading data, because without it, as much as you would like to express reading from Kafka as a composable regular function, you cannot if that function is required to be indivisible per element. And Splittable DoFns remove that limitation. That is pretty much it. Questions, please. Okay. Yeah, OK.
There in reading data, but can you mention anything about writing data? Those ideas of sort of decomposing.
Yeah. OK. So the question was that the talk was mostly focused on decomposing the task of reading data, and what about writing data? The task of writing data is, first, it's a little bit less interesting because it does not have the same challenges that reading. As for composable primitives that you can have there, for example, when you're writing to files, you can think of it as first group records by the name of the file you want to write them to, then actually write to temporary files, and then atomically rename temporary files to final locations. And this atomic rename operation is obviously reusable in other contexts, and the grouping itself is reusable in other contexts, and so on. Yes? Mm-hmm. Okay, the question was, what are the temp files that I've been talking about? So the anatomy of writing output to files is that you take the records, you write them to temporary files first, wherever they're located. You might have a temporary directory somewhere, or the user might tell you that put your temporary files over here. And then when you've written all of them and you're sure about which ones of them are not corrupt or incomplete, then you take those and rename them to the final locations that the user asked, and you delete the rest.
So that be interpreted as temporary files, and then the permanent file is a copy into a data warehouse.
Sure. Yeah, that's one way to look at it.
Like they're staging tables.
Mm-hmm.
Staging files.
Yes, one way to think of these temporary files would be that they're staging files, but this is really just an implementation detail of a particular case that is writing files. It's just the way it's typically done. There is nothing deep to it. More questions? Yeah. Mm-hmm. Mm-hmm.
So maybe you want to batch it to 100, so if you get less than 100 milliseconds, you want to process that anyway to ensure that things are
mm-hmm. Okay, so the question was whether this idea of splitting applies to temporal splitting in the sense of process 1 second of data, then process another second of data, and so on, right? Okay, so this is, I would say that splitting over processing time is more of an operational concept, whereas this is more mathematical, and there is no strict way to define what it means, like what is the first second of data and what is the second of data. So I would not advise to try expressing that kind of splitting in this way, because the semantics of decomposing restrictions into smaller restrictions are really critical, and this is the point where you're at the biggest risk of introducing a data loss bug. If the way that you split things does not always correctly adapt to the original thing. A better way to think about splitting in time is just so-called triggers in Beam, or I think it's called the same in Flink. So it is more of an operational concern, more of an instruction. Whatever data arrives into this operator, process it every 1 second. Yeah. Yeah.
So one of the questions that I had about streaming versus batching was backfilling of old data that we have in one of the, and the most recent answer on Stack Overflow from one of the core creators was that Beam does not have a established design pattern for backfilling. Is the splittable do function? Is there an idea of like how we can accomplish backfill processing with this pattern?
Okay, the question was that one of the Stack Overflow questions about beams. One of the answers from a core Beam committer says that Beam currently does not have a design for this kind of big backfilling, and whether Splittable DoFn addresses that. Yes, this is one of the main motivating examples behind Splittable DoFn, because it can express this kind of thing that is like a huge backlog with a continuously growing end of the backlog. And its API allows you to have both the best of both worlds. It allows you to exercise dynamic splitting and autoscaling and so on while you're processing the huge backlog. And then it allows you to also talk about the future backlog, for example, if you want to autoscale the streaming part. Yes?
How do you monitor this?
The question is, how can we monitor Beam pipelines? That depends on the runner. So Beam itself does not define an API for monitoring, but different runners implement it to different extents. Or more like Beam does define a simple API for monitoring called metrics that are just aggregated across operators. For example, Dataflow has a user interface that shows you all the transforms in a nice pretty graph, and when you click on them, you can see how many elements got into it and how many elements it produced and how much time it took. There's all kinds of things you can do there, and different runners do different things there. Yes?
Do you guys support any kind of high-level query language on top of Beam API? Because sometimes API is not easy for some people to use.
The question was about whether there is going to be a high-level query language on top of the Beam APIs. Yes, the effort for SQL as a first-class way to program Beam is currently well underway. Yes?
You mentioned earlier that the Beam model, you have your SDK, you have the Beam model, and you have the filters. How is the Beam model currently serialized? Is it actually the target serialization? Is it just a bunch of Java instances?
Okay, the question was that I said that different SDKs sort of assemble the same portable description of the pipeline, and how does this description look like? It looks like a proto buffer that contains like a list of transforms and the way they're wired together. And of course, for example, if your transformation includes transforming something with a Java function, it contains the serialized form of that function. But the Beam model does not care that this is a serialized Java function. The entity that will care about that is the runner that will see that part of the portable description and see, oh, this is a Java function. I'm going to need to start a container with the user-specified jars and ask it to execute this function. Yes?
Do you lose any benefits of data locality by doing it this way because it's not aware of where the data is when you start processing for HTML?
Okay, the question is whether we lose any benefits of data locality if we think about things this way. I have two answers to that. First, I don't think we should worry about data locality that much. It's probably better to have a file system layer that doesn't care about it, such as any cloud file system. The second answer is, okay, probably three answers. The second answer is yes, we do lose these benefits, but that's because we don't think they're all that important. The third answer is that traditionally, this kind of locality is provided only on the native read API. But for pretty much anything that is provided on these native APIs, at some point you start asking yourself, I wonder if it should also be provided on everything else. Like suppose you've written a flat map function, a Pardue that reads data from files in HDFS, and then you would like that function to have locality. So I think generally it would be reasonable for all of the programming model to contain these kinds of requirements. Just currently, Beam does not describe this because nobody has thought that it is sufficiently necessary at this point. But the main point is that all of these special things are not really special and either apply to all of the programming model or should not exist at all. All right, teams, I'm out of time. Thank you.